Okay, so we left off last time talking about beam deflections. I think we did a simply supported beam. Get the right pen here. I believe we went through a process where we had this simply supported beam, and we had a constant distributed load on it like this, and we came up with the deflection. We figured out what the shape of that curve was for the deflection and figured out what values it would have. And to do that, we had to take one section through there because it was continuous all the way across. And we went through that, and you can look at the notes from last time. Well, I'm not going to go through this problem in its entirety, but let's say that we were given a problem like this where we had a concentrated load. We'd actually have to go through that process twice. We would have to take a section here and go through it, and take a section there and go through it. Now, if the load happened to be at the middle and we saw some symmetry, we could actually just do one side and mirror it over. But like this one, where the load is not in the middle, we would have to go through this. So we'd have a set of equations here. Let's talk about equation maybe 1. And then we'd have a set of equations here, equations 2. So we'd have a moment equation here that would then lead to a deflection equation. We'd have a moment equation here that would lead to a deflection equation. Hopefully those equations would meet at this point, that they would have the same value at that point, because there shouldn't be a discontinuity there. The thing that I want to really bring out is in solving these equations, we have to have boundary conditions here, and the boundary conditions have to be in this region. You can't use boundary conditions from over here for this equation. So if you're looking at the equation on the left-hand side, you have to use boundary conditions from the left-hand side. If you're using the equation on the right-hand side, you'll have to use boundary conditions for the right-hand side. And you've got some homework problems and examples in the text that go through that. But I wanted to bring that up. When you're working on equations that are pertinent to this region, you got to use boundary conditions that are in that region. Let's see. The next thing I wanted to look at is, let's see, maybe we'll do another example here. Let's see what I got. Yeah. Well, maybe I'll just finish this up. So you got to use boundary conditions where your equation is valid. Let me try another problem which gets us into the notion of superposition. And let's say it's a cantilever. I don't think we've done a cantilevered problem yet. And it has a distributed load over the cantilever, and it's also got a concentrated load at the end. And I'd like to come up with an expression for the deflection on this thing. And we'll go ahead and do it like we did the last problem. I'm just going to go ahead and take a section through this thing. With this one, we'll only have to take one section. So I think I'll take the left-hand side. Or, no, not the left-hand side. I think I'll take a right-hand side. I don't know that there's a lot of difference in ease. This one, the algebra may get a little uglier, but I don't have to solve for the reactions. So I'm going to take this, and I'll put that load P here. We'll put the distributed load that remains here. Now, our deformation sign convention, the shear would go up. I'm not really interested in that, but the moment would go this way. I'm very interested in that. And this distance here is the distance L minus x, right? Okay, because x is going to start at the left-hand side and go to the right-hand side, so the distance remaining would be L minus x. So if I look at summing the moment about the cut, setting it equal to 0, I have what? If I take clockwise as positive, I'm going to have m plus p times L minus x, plus, then if this is w, I'll have w times L minus x, and that x is going to act through the center of that, so it would be then times L minus x divided by 2. So that's what I would have there. I could say then that this is minus m, moving the m over to the other side. Now it should be handy because our equation deals with minus m for the deflection, is equal to p times the quantity L minus x plus w over 2 times, what are we going to have here? L squared minus 2lx plus x squared. It's a little bit of algebra there as I square those pieces. And I could keep working through my algebra here. The moment is going to be p times L minus p times x plus WL squared over 2 minus WLX, because the 2's cancel, plus WX squared over 2. And we know that minus m, our general equation is minus m is equal to EI V double prime, right? So I could set this then equal to EI V double prime and go about solving that equation right there. Questions with that? You could have taken a section and looked at the left-hand side if you wanted to. Like I said, I took a section of the right-hand side. Now, because of this, I'm going to, well, my equation should be good the whole way. I mean, this equation is good for what? Should be good for x between 0 and L, right? Which is important because that's where I've got to select my boundary condition from. Here in a moment, I'm going to integrate this a couple times, get a couple constants of integration. I'm going to need some boundary conditions, and I will have to select my boundary conditions over those same ranges. That's what we were talking about here on this first page. If you have an equation that's only good over this region here, that's where you'd better select your boundary conditions from. Well, my equation is good over the entire region, so I shouldn't have much trouble selecting my boundary conditions. Questions of that? So if I integrate this thing, I'm going to come up with PLX minus PX squared over 2 plus WL squared x over 2 minus WLX squared over 2 plus WX cubed over 6 plus my constant of integration. I'll say C naught is equal to EI, and then V single prime is really your slope theta, isn't it? That's V prime. So I might, at this point, apply my a boundary condition. I could note that one of my boundary conditions is that, and I can use boundary conditions over the entire thing. So I know the slope back here, if I were to draw the deflected shape on this, what this looks like when it deflects is probably going to be something like this, right? Where we're going to get maximum deflection at the free end. But here we have 0 rotation, so we've got 0 slope. So I should be able to say that theta at x equals 0 is equal to 0, isn't it? So if I go through that, I have a 0 minus 0 plus a 0 minus or plus, doesn't really matter, a 0 plus 0 plus C naught is equal to EI times 0. So I conclude then that C naught is equal to 0. So my first constant goes away, and if I was careless in my integration and didn't put that constant in this case I would have lucked out, but that's not always true, so be careful with that. Questions before we move on? Well, that worked so well, let's do it again. So I've got then, I need to go through this again. I'll do it this way. So I can say differentiating this, or integrating. I'm going to integrate again. So integrating again, you got PLX squared over 2 minus PX cubed over 6 plus WL squared x squared over 4 minus WLX cubed over 6 plus wx to the fourth divided by 24. C naught was 0, so I don't have to worry about that. Say that's equal to EI times the deflection V. Okay with that? Let me double check.
Should there be another constant integration?
Oh yeah, I probably should put one in there. So we'll say C1. Yeah. Plus C1. Good call. So I got my constant of integration. Let me double check my terms here. And what I'm checking for is these terms here with the P. Those are from the concentrated load, and they should all be of the same order. So if I have the P in the term, there is L times x squared, so that's a third order term. This is a third order term because it's x cubed. Then the terms with W, they don't necessarily have to be the same number order of the same order as these terms, but they need to be all the same in themselves. So this one has a W in it. It looks like it's a fourth order term, right? Wx cubed, that's fourth order. So that's fourth order. Okay. So that can keep us from hopefully making too many silly mistakes. Well, I need a boundary condition here too, don't I? So let's see. We could say that the deflection, going back and looking at this picture here, we notice at this point that the slope theta is equal to 0. We also know that the deflection should be equal to 0. So if we write that in terms of this, the deflection at x equals 0 should be equal to 0. So I have 0 minus 0 plus 0 minus 0 plus 0 plus C1 is equal to 0. So I get that C1 is equal to 0. So had I continued in my mistake, I would have lucked out on that one, but that's not how we want to do math. So, questions with that? Okay. So let me rearrange this a little bit. Let me talk about the deflection, V. I could say that's 1 over EI. And then I'm going to group up my terms. I'll put the P terms together. We'll have PLx squared over 2 minus PX cubed over 6. I'm going to add to this 1 over EI times, what do we have here? The W terms. WL squared x squared over 4 minus WLx cubed over 6 plus WX to the fourth over 24. So I just broke those apart. And now maybe I'll factor some out of here. We could say that this, let's see, if that was 6, that would be a 3. So we could say that the deflection V is PX squared divided by 6 EI. What we have remaining is going to be a 3L minus X. And then here we have, we'll pull a WX squared out, and we'll have 24 EI, and we'll then have, what, 6 L squared minus 4 LX plus an X squared. Okay, so those are terms, and we can see those very clearly, what terms contribute to, or what terms are the contribution from the concentrated load and what terms are the contribution from the distributed load. This also gives us a good way to check this problem, and probably in the future a good way to do this problem. Your boss probably does not want to pay you to take this fun trip through calculus and boundary conditions and things like that, so we'll talk about how we can use superposition. But we could check this. If you go to the Appendix C in your textbook, and that's been the same for a lot of editions. It's probably on a different page number, so I'm not going to note the page number. And it's a little small to see here, but if you flip to the back of the book, we've got simply supported beams here. We've got cantilevered beams here. So I want to look at the cantilevered beams, and here is the one with a concentrated load at the end, and here's one with a distributed load. They don't have exactly ours, but hopefully with the principle of superposition we can put these together. So we have here that this one says that it is minus px squared over 6ei times the quantity 3l minus x. So I'm looking right there. And the only thing that we differ by is a negative sign. So I think we're okay with this term. We differ by the negative sign because we took positive down, your author took positive up. Then if we look at this one, we come up with the expression minus wx squared over 24ei times the quantity x squared minus 4lx plus 6l squared. Slightly different ordering here, and then the negative sign again. Your author takes negative differently than we do, so I think we're okay with this expression. But probably the most important part of this is in the future we can use superposition to say that a problem that we started with that looks like this we could say was the same as taking a problem like this and adding to it this problem there. So that's exactly what we did, and you can see the equations. This one, probably should have done them in different order, but this one is that piece and that one is that piece. And you can get quite sophisticated in this superposition, and after you go through looking at how you can excuse me, spend quite a bit of time in the derivation of these things, you probably want to try and get more out of the tables. You could first find a table that was more complete, but probably no table is going to have all of the situations that you want. But let me talk about an example that your author does. But this is page 4. Your author does an interesting example like this. Now, I'm not going to go through this. I'm just going to kind of lay it out a little bit. But you have a simply supported beam that has a cantilever section. Over the simply supported section, you have a constant distributed load. Over at the cantilever, you have the concentrated load. And if we look at the tables here, so I'll make this page 6. If we look at the tables there, we don't have anything like that. We've got simply supported. I don't have anything that then continues on with a cantilever. So can I use the principle of superposition to put these together? Yeah, you actually can. And let's say that you were interested in the deflection out here. What you're going to have to recognize is that this distributed load here is going to cause that beam to deform like that, isn't it? Okay. And so what you're going to have to start with is then you're going to find the slope at this point. So you get your theta here, and you'll start with a cantilever beam that is then rotated like that, and that's going to deform back like that. Okay. Because as this deforms down like this, that's going to cause this cantilever beam to not deflect as much. I mean, if it just started from this point here, it would deflect down. Its net movement may still be up. This is actually a big deal. When you go to design a beam, let's say that you do a beam for a structure that has a cantilever. So it's not exactly this example, but maybe it has something like this. And a lot of times the deflection out here can be a problem because the deflected shape of this thing ends up looking like that, and you get quite a bit of deflection out at that free end. Okay. Now, if the question comes up here, you want to try and find the deflection there, what you're going to have to do is you're going to have to look at the model a little bit differently and say, well, I have this beam with a distributed load on it, and what am I also doing? I'm putting a concentrated load here and also a moment like that, right? Do we have an example that we could use for that? Yeah, here's a simply supported beam with a moment applied to it. So you should be able to do that. So the example, it's out of your textbook. Again, I won't give you a page number, but it's a good lesson in this. Is example 1214, and the authors usually don't change the examples very often, so it'll probably be on a different page number, but no matter what edition you have, you'll probably find that as 1214. And it goes through this principle of superposition a lot more so than this problem. I mean, this is one of the easier superposition problems where we just literally superimpose those on top of each other. This one really takes it to the next level where we can start to look at that. Questions with that? Well, another way that I'd like to look at this, So I get to page 7 here. So let's say we go back to a very simple, simply supported beam. We could make the same argument with a cantilevered beam, but we'll keep life easy and say that it's a simply supported beam, constant distributed load. And we'd have a shear diagram. If I look at the shear diagram, we've done this many times. There's what our shear diagram looks like. That's capital V, okay, the shear diagram. And then the order is going to continue to increase, isn't it? So if I look at the moment, this was constant, this is linear, so the moment is going to be second order. And again, that's that capital M, the shear and moment diagram, which most of you have well at hand. Then if we continue on, the slope, if this is, what, in this case, second order, the slope is going to be third order. And we'd see the slope at the middle. I mean, if we draw the deformed shape of this thing, it looks something like that, and we have zero slope at the middle. This is third order. And then if we finally get to the deflection, what's that look like? That's going to look something like that, very flat and fourth order. That's going to be our deflection, and that's exactly what I drew up there, and you hopefully would imagine looking at that. Well, mathematically, let's see what these are. We've been talking about the deflection. That's V, so that's pretty straightforward. And then the slope theta, we said that was V prime, or maybe a more careful writing of that would be dV dx, same as V prime. And then the moment, we could say was what? Minus EI times the second derivative of V with respect to x, right? And then what? I can go one more, and I could say that, I guess I can go two more. I could say that the shear, that's capital V, is equal to minus EI times the third derivative of the deflection with respect to x. And I guess that can get me up to the load, which I could say was Q or W. So Q or W is going to be equal to EI times the fourth derivative of V. Not a very good fourth. There's the fourth derivative of the deflection with respect to x. So for our discussion with the deflection, we've started at this point, and then we integrated to get down to here, and then we integrated again to get down to there, and we had a boundary condition here, and we had a boundary condition there. We could, if we wanted to, and I'm not going to go through it, but we could, if we wanted to, start up here with this expression, and what would we do? Integrate 4 times, and then we would need what? 4 boundary conditions? And we could get that. So if you really don't like the moment, you can actually start with the expression for the load. Now, it's probably a lot easier to think about this like this, but I wanted to try and point this out in a little more panoramic view. Now, the one thing to be careful of is your author has different signage on this. They have a negative sign on this. They have a positive sign on that, a positive sign on that, and a negative sign on that, because they've taken different conventions as positive and negative. But you really, yes?
Your shear, that's the third derivative?
Down here? Yes, thank you. Was that your question?
Yeah.
Okay, great. Thanks. So while we don't do it very often starting up here, you actually could if you wanted to. So we've talked about how to do this mathematically. We've talked a little bit about how to do this with tables and getting the most out of the tables in terms of superposition. You can do a lot more things than you see on these tables when you start to combine the tables, or you get better tables, or you make your own tables. Usually when we were studying something, after we studied, we would talk about stress and strain, and then we would talk about deflection. And then after we talked about deflection, we would talk about statically indeterminate problems, right? So I want to wade into that, or at least get started with that. So if I look at statically indeterminate beam problems, and a couple cases come up. Let's say that we have a propped cantilever. So we have this cantilevered beam here, and we put a prop here on the end of it, and we could apply, maybe we'll just say a distributed load. And this comes up in real life all the time. So let's say that we've got a building, and they've extended out the joists here to make some sort of a patio from the second story, like this. And we need a little more support, so we put a column out here supporting this thing. Very, very common arrangement. Okay. Well, if I look at a free body diagram of this thing, I'm going to have a reaction there. I'm going to have a supporting moment there. That's all well and good. But out here, I've got this roller, and I'm going to have a second reaction. So maybe I'll call that reaction 1. I'm going to call that reaction 2. And if I look at my equations that I have at my disposal, I could sum the moments, setting that equal to 0. Sure enough. I could sum the forces in the vertical direction, setting that equal to 0. I could sum the forces in the horizontal direction, setting that equal to 0, and I'd get 0 equals 0. So I really have a trivial equation there, because I don't have any forces in the horizontal direction, right? So what am I left with? I'm left with 2 equations at how many unknowns? 2 equations, 3 unknowns. Okay? So I have a statically indeterminate problem that comes up all the time. Yeah?
Wouldn't that moment on the side though just be taken up by the R1 R2?
No? Be nice if we could do it easier like that. Yeah. I guess the answer is no.
That roller wouldn't relieve the moment that's on the end of the part?
Because the moment presumably is going to be working in conjunction with R2. I mean, if you want to say that the moment is 0 and we replace it at R2, that would be a little bit like coming in here and we cut these off and we put this here, but that's yet a different problem. Okay. Another one that comes up an awful lot is a continuous beam. So we take this beam and I put it over a couple of rollers. Okay, and have a distributed load here. Like that. Okay. Where do we get that? Well, let's say that you've got a beam and you've got some openings. Maybe this is a deck or something. So you have people up here, and you're going to support this here. Maybe it's some sort of a patio or something. You support it on this column, you support it on this column, and you support it on that column. Could we get that? If we got enough people up here, we could get that load. Or you might say, well, there's no load there. Well, what happens when they walk over here? Sometimes we have to look at a pattern load where you only have a load on one side or the other. Okay. So all different possibilities. But any of them are going to be statically indeterminate, because if I look at a free body diagram of this problem, what's the free body diagram look like? Now I got a force there, I've got a force there, so we can say this R1, R2, R3, and R4. We of course have this distributed load there. So if I sum the moments, setting those equal to 0, that should work. Some of the forces in the vertical, that should help. Some of the forces in the horizontal is equal to, that's going to just be R1, isn't it? So what am I left with? I've got then 2 equations. I know what this is. That's equal to 0. How many unknowns do I have? 3 unknowns. So I have 2 statically indeterminate problems that come up all the time in our structural work, so we want to be able to deal with those. So let's see how to make that work. We're going to do them like we've done all problems, and it's probably the easiest to recognize in a beam problem than in an axial problem, or certainly in a torsional problem. Torsional problems are kind of hard to visualize. But if I were to take this propped cantilever, this one here, and look at what we're going to do to this. So we take this thing, and I have this moment here, and we'll say this reaction 1 and this reaction 2. And I'm going to say that this is going to be equal to the situation here where I look at, maybe I'm going to change this just a little bit. If I decide to take this one over here as redundant, so I'm just going to say that that is redundant, and I remove that redundant one, what's this going to look like? This thing's going to sag down, right? You probably recognize that. I mean, this would be like back over here. You have someone and they want a better view and they come out and they propose cutting the column out. And you'd go, don't cut the column, because what's going to happen? It's going to sag down, right? And we would get some deflection here. You would have some deflection. We'll say delta 1. We're all experts now in calculating deflections of beams. But we're going to have to add to this. What's going to happen here? You got to put this one back in, and if you take this distributed load off and you put this one in, what happens to this thing? You get a deflection like this, where it deflects up, where this is delta 2 due to this R2. And what do we know about delta 1 and delta 2? They have to be equal, don't they? Okay. So we'll put those two together. And we'll go through at least one of these in quite a bit of detail. How can I handle the other one where I look at a continuous beam? Let's look at this one, see what that looks like. Well, what we're going to do is we're going to take this thing, and we won't worry about the horizontal support there. I'll leave that off. You said it was 0 anyway. I'm going to say this thing's equal to, I mean, if we were to come in and remove this one, someone drives in and they hit it with a car. We'll blame the mechanicals here. Okay, they hit that with a car and it knocks out. What do you think is going to happen here? Probably sag down, right? Okay. Only the drunk people will be left on the deck. So it's going to sag down rather significantly. So apparently I've taken this one as my redundant. Okay? And it sags down and I can get some delta 1. I can figure out how much it sags down, right? And I then add the situation to this. If I hold these here, and you have to think about these being constrained, and just put the one on in the center, what does it do? You get something like this, right? And you would have this fixed like this and a roller here. Sometimes you have to think about a roller top and bottom. Okay, you put your redundant one in here and you get some deflection here, delta 2. What do you know about delta 1 and delta 2? They have to be equal to each other. So in both cases where we set these deflections equal to each other, that's your last equation that you need to come back and solve the problem where you have one more unknown than you have equations. So that's what we'll do. We'll actually apply it to this problem here. That's always a good example to look at. And it's kind of interesting what we learn from that. So that'll be a good thing to do. I'll record that lecture tomorrow, and you can look at that on Wednesday. Take care till then.